In this lesson, we study the single-phase bridge full-wave rectifier. A bridge uses 4 diodes and a transformer secondary without a center tap. We will trace both half cycles, relate the ideal and practical output voltages, determine the peak inverse voltage, and then derive the transformer utilization factor. The average value, RMS value, ripple factor, and rectification efficiency are the same as for the center-tapped full-wave rectifier, so we will state those results without repeating their derivations. By the end of the lesson, you should be able to trace the conducting diode pair during each half cycle and explain why load current retains the same direction. You should distinguish ideal output voltage from the practical result that includes 2 forward diode drops. You should determine the peak inverse voltage across each non-conducting diode. You should also recall the standard full-wave values for average output, RMS output, ripple factor, and maximum rectification efficiency. Finally, you should be able to derive and interpret the transformer utilization factor of an ideal bridge rectifier. During the positive half cycle, the upper end of the transformer secondary is positive with respect to the lower end. Diodes D1 and D2 are forward biased, while D3 and D4 are reverse biased. Trace the current from the positive end of the secondary, through D1, through the load resistor from top to bottom, through D2, and back to the negative end of the secondary. The important observation is the polarity across the load, its upper terminal is positive. Therefore, this half cycle produces a positive load voltage pulse. When the secondary voltage reverses, its lower end becomes positive. Diodes D3 and D4 are now forward biased, and D1 and D2 are reverse biased. The conducting path is from the lower end of the secondary, through D4, through the load from top to bottom, through D3, and back to the upper end of the secondary. Although the transformer current reverses, the load current again flows in the same direction. This steering action of the bridge converts both input half cycles into positive load voltage pulses. These two figures compare the ideal and practical bridge models. In either half cycle, one diagonal pair conducts, so the complete secondary winding supplies the load. Under the ideal model, the magnitude of the secondary voltage appears across the load. In the practical silicon diode model, 2 forward biased diodes are in series with the load, so their drops reduce the output. If Vm is the peak of the complete secondary winding, the ideal peak output is Vm, while the practical peak is lower by approximately 1.4 volts. A practical bridge always places 2 conducting diodes in series with the load. For silicon diodes, each forward drop is approximately 0.7 volts. The 2 drops therefore subtract about 1.4 volts from the instantaneous secondary voltage whenever the bridge conducts. At the peak, Vp out is approximately Vp secondary minus 1.4 volts. This is the main voltage penalty of the bridge compared with the center-tapped rectifier, where only one diode lies in the conducting load path. For the ideal bridge, the load voltage and current have the same full-wave rectified shape as in the center-tapped full-wave circuit. Therefore, we do not repeat the average value, RMS value, ripple factor, or rectification efficiency derivations. With Vm and I'm defined as peak load voltage and peak load current, VDC is 2 Vm by pi, and IDC is 2 Im by pi. The RMS values are Vm by root 2 and Im by root 2. The ripple factor is about 0.483, the ideal maximum rectification efficiency is 81.2%, and ripple frequency is twice the input frequency. To determine peak inverse voltage, consider the instant when D1 and D2 conduct. Under the ideal model, each conducting diode is a short circuit. The non-conducting diodes D3 and D4 must then withstand the reverse voltage shown in the figure. The maximum reverse voltage across either diode equals the peak of the transformer secondary voltage. Since the ideal peak output also equals that secondary peak, the result can be written as PIV equals Vp secondary, which also equals Vp output. With practical diodes, one conducting forward drop lies between the reverse bias diode terminal and the active end of the secondary. Thus the reverse stress is Vp secondary minus 1 diode drop. Because the practical output peak is Vp secondary minus 2 diode drops, the same result is Vp output plus 1 diode drop. For silicon diodes, PIV is approximately Vp output plus 0.7 volts. This plus sign is essential, it follows directly from the two different voltage drop paths shown in the circuit. Transformer utilization factor measures how effectively the transformer secondary voltampere capability is converted into useful DC load power. We define TUF as PDC divided by VSRMS times ISRMS. For the derivation, assume ideal diodes, a resistive load RL, a sinusoidal secondary voltage Vs equals Vm sin theta, and a peak load current Im equal to Vm divided by RL. Here Vm is the peak of the complete bridge secondary winding. We will evaluate the numerator and denominator separately. The DC output power is the product of the average load voltage and average load current. From the standard full-wave results, VDC equals 2 Vm by pi, and IDC equals 2 Im by pi. Multiplying these quantities gives PDC equal to 4 Vm Im divided by pi squared. This result uses the DC component delivered to the load, not the total RMS heating power. Keep that distinction in mind, because TUF asks how much useful DC power is obtained from the available transformer voltamperes. The complete secondary winding carries a sinusoidal alternating current. Its direction reverses every half cycle, while its magnitude equals the load current. Therefore, the secondary RMS voltage is Vm divided by root 2, and the secondary RMS current is Im divided by root 2. The transformer secondary voltampere rating is the product of these RMS quantities. Multiplying gives Va secondary equal to Vm Im divided by 2. Unlike a center-tapped rectifier, the bridge uses the entire secondary winding during both half cycles. Now substitute the useful DC output power and the transformer secondary voltamperes into the TUF definition. The factors Vm and Im cancel. Dividing 4 over pi squared by 1/2 gives 8 over pi squared. Numerically, this is 0.8106, commonly rounded to 0.812, or 81.2%. The high value results from using the full secondary winding and both half cycles. This is the bridge rectifier's main transformer utilization advantage. Rectification efficiency and transformer utilization factor answer different questions. Rectification efficiency compares DC output power with the AC power entering the rectifier. TUF compares that same DC output with the transformer's RMS voltampere requirement. In a bridge, the whole secondary winding carries current on every half cycle, so the secondary-only TUF reaches about 0.812. A center-tapped full-wave rectifier uses alternate half windings and therefore has a lower transformer utilization, even though its ideal ripple factor and rectification efficiency are the same. Consider an ideal bridge rectifier supplied by a 12-volt RMS secondary and a 100-ohm load. The secondary peak is 16.97 volts, so the peak current is 169.7 milliamperes. The average output voltage is 10.80 volts, and the average current is 108 milliamperes. DC output power is about 1.167 watts. Secondary RMS current is 120 milliamperes, giving 1.44 voltamperes. Their ratio is approximately 0.810, in agreement with the theoretical TUF. A bridge rectifier uses 4 diodes, with 2 diodes conducting in each half cycle. The bridge keeps load current in one direction and uses the complete transformer secondary without a center tap. 2 forward diode drops reduce the practical output peak. Each diode requires a peak inverse voltage rating approximately equal to the secondary peak. The ideal average, RMS, ripple factor, and rectification efficiency results are the standard full-wave values. Most importantly, the ideal transformer utilization factor is 8 over pi squared, approximately 0.812. Use this final comparison to place the bridge in context. Both full-wave circuits have the same ideal average and RMS outputs, ripple factor, ripple frequency, and maximum rectification efficiency. The bridge needs 4 diodes and incurs 2 forward drops, but it avoids a center-tapped secondary, requires only Vm peak inverse voltage per diode, and achieves the highest secondary transformer utilization. When reading the center-tapped column, remember that Vm is defined as the peak of 1/2 secondary. For the bridge column, the same symbol represents the peak across its complete single secondary winding.